Okay, so we know about the null space. There is another space that we can obtain from um, this is column space, row space, null space. Okay, so this is null space of A, but we can also look at the transpose of A. So if we take a null space, the transpose of A, we get this 1, 2, 4. Okay, so with this we can look at the null space of this matrix. Okay, so it's a set of vectors x1, x2, such that. Okay, so if we solve this linear system and take all the solutions, we have another matrix or another space. We refer to this as the left null space of A. So now we arrive at this four subspace originating from A. Okay, the first two are span, so row space and column space. So these are the space spanned by the rows of A and the columns of A. Okay. And we have now space of A. So these are the vectors that Ax equals 0. And also we have the left now space of A. So these are the vector that A transpose y equals 0. Okay. And when we have these many spaces, we can look at the dimension of them. Okay. Previously, we look at the rank of A, and that's the dimension of the column space. Say rank of A equals R. So the dimension of column space and row space of A equals to R. They are both equal to the rank of A. The null space of A. Okay, the null space of A are those variables that you can set and use to remain in after you multiply with A, you get to 0. Okay. The dimension of null space, if we look back, okay, what is the dimension of the row space of A? 2, right? And the null space, the dimension of null space is 1. Okay, so you can think of it this way. If the rank of A is A, if you look at A in terms of linear systems, okay, we have 3 variables, okay, but the rank of A is 2. That means you only have 2 equations. You have 3 variables, you have 2 equations, so you are free to move 1 variable. So that's the dimension of the null space. Okay. Now, if I have another matrix with rank 1, okay, suppose I have a matrix 3 by 2, but the rank is 1. What is the dimension of null space? If I have 3 variables, I have 1 equations, I can set 2 variables. Okay. These 2 variables would become like when I compute the null space, these 2 variables will be like you get vectors that depends on 2 variables, and if you split them into a span, you have the space to be a span of 2 variables. So the dimension of null space become 2. Okay. So from this idea, you can see that the rank of the row space, okay, if the rank of a row space is large, the null space will be small, because like the rank is like the number of good equations that you have. Okay, you have n variables. If the rank is n, then the null space, the dimension of the null space is 0. You only have unique solutions. But if you have n variables and the rank of the matrix is less than n, you can move around in the null space, and the dimension of the null space is basically n minus r, and the dimension of the left null space should be m minus r. I'm not going to prove you this, but you can see if the matrix, if you have okay, let's see a concrete example. If you have n by n matrix, okay, if the rank of the matrix is n, so it means when you do Gaussian elimination, you have matrix that look like this. Okay, it's just diagonal matrix on upper triangular matrix. Okay, you can see that the only way you get 0 is to assign 0 to all the variables. Then the dimension of null space will be 0. Okay, but if you do the Gaussian elimination and then you end up with some empty rows, right? Some empty rows here, and you have r row left. Okay, so that's the rank of the matrix, and this is n minus r, right? So this is the dimension of the null space. So basically, the number of variables that you can set while remaining, while ensuring the linear system remains satisfied. Okay, so we have this relationship. You have 4 subspace. Okay, they are connected by the rank. Okay, the rank of the matrix, both row rank and column rank, is the same, and that's the dimension of the row space and column space. And the leftover dimensions of the row space will be the dimension of null space, and the leftover dimension of the left null space will be n minus r. Okay. Okay. So let me draw you a picture. So so you have a matrix m by n, right? So there are two sides of this. One is the span, when we talk about span. The other is when we talk about homogeneous system of linear equation. Okay. When you look at the span, you have row space. So you have each row, I. So this is span R1 to Rm. Okay, and each vector is of length, is of size n. So this span will be subset of R to the n. If you take the columns, okay, you have column space. This is the span of the column C1, C2 up to Cn. Each column is a vector of size n. So this will be a subset of R to the n. Okay, that's the 2 space we're talking about. Now, if you look at the matrix as a linear system, okay, so you have Ax, so this is A, right? So you have Ax equals 0. Okay, so this set of solutions, so that's now space of A. Okay, and also if you look at the transpose of A, so you have another equations, A transpose times Y equals 0. This set of vectors is the null space of A transpose. Okay, and each vector, if you look at this as a linear system, X has n variables. Okay, so you have n columns. Each column will be a variables. So this will be a subset of R to the n, and this will be a subset of R to the m. Okay. Okay. So you have four space now. Okay. So let me highlight that. This first space, row space and column space, and null space, and left null space. What are the dimensions? So the dimension of this is R, that's the rank of the matrix. Dimension of this is also R. Okay. But you can see this is a subspace inside R to the n. So the whole space has n elements, right? Each vector has n elements. So it's subspace of R to the n. But the dimension is only R. Okay. So the leftover dimensions will belong to the null space. So dimension of this will be n minus R. Same thing here. Dimension of this is a subset of R to the m, right? So you have m variables, but the column space only span R of them. Okay. So the leftover dimension is m minus r. Okay, so that's the three space that we are talking about. Okay, they are related by matrix A. Okay. Now I'll show you another picture of this. Okay, when we think of A as a function. Okay, currently we think of A as a matrix. Okay, when you look at A as a matrix, you can view A as a set of rows or a set of columns. From that you have a span and so on, right? But we will now look at A as a function. You see that soon. This takes us into what we will learn about linear transformation or linear functions. Okay, I'll talk about that